Hello, students. We are going to do some operations on decimals. And operations on decimals, remember, what are decimals? They are fancy fractions. So all the rules you learned about fractions are going to apply here, which is fantastic. A lot of this does tend to take place. They build decimals in grade 4. Grade 5 is when they tend to do the operations, and you can see that here for the Common Core. And so let's take a look. You have a couple models. You could model this either with the poker chips or with base blocks. Totally fine. They also have decimal strips, is what they call them. And so those strips are like little pieces of paper that go down to the tenths and the hundredths. And so you can kind of shade in those strips to kind of make it work out. But again, if what you're doing is and this is a great way to kind of think about and visualize it, is with the base blocks, is you can kind of say if my whole object is the square, which is made up of 100 cubes, then a tenth of that would be a strip or a rod, and then the units cubes would be my hundredths. So when you look at this is the number 2.16, and they're adding 1.73. So 2 and 16 hundredths plus 1 and 73 hundredths. And what you're doing is you're adding the like objects together. So all of these little cubes, they all add together. And then don't forget, just like we did with the chips, if we have too many of them, we regroup. In this case, no regrouping is necessary, so the final answer is 3 and 89 hundredths. So kind of basically what they're doing, if you can kind of see, is they're rewriting these into fractions and then adding the like denominators together to make it easy, and then recombining at the end of the day. So there's nothing wrong with that at all. It might make it a little long, but we'll see. There might be some shorter ways around it. Okay. So if you had two different looking decimal numbers, and I'm going to show you kind of, here's the common mistakes, right? If I had this number, 2.1, and I'm going to add 1.73. If I was doing that, the most common mistake that students make is they treat this like whole numbers. So they would write 1.73 plus 2.1, and then they would add them together straight down, 4, 9, and 1. Now, hopefully you're able to at least say, hey, there's no way that I could start with something bigger than 2, add something bigger than 1, and get back to and get back to something less than 2. That just shouldn't happen. All right, so we've got that piece that's definitely that shouldn't happen. But what we want to do is we want to think about these as place values. Okay, so place values, the ones need to match up with ones. The tenths need to match up with tenths. So when we line them up, the rule is typically we line up the decimal places, but we don't want to memorize a rule for no reason. We want a reason for it. And so really, when you think about it, all we're doing is we're just putting our values that are the same together. And so you could write it this way. Okay. But I will tell you, most of the time, at least for students who are struggling, it's better to rewrite it so that you put the additional 0 in there. And that way they can kind of think, I always want to make sure everything's all lined up. Decimal places are all lined up so that if I add tenths, I'll have 8 tenths, 3 hundredths, and 3 whole units. Okay. Phew. All right. That's adding. Subtracting is the same, by the way. Subtracting is the same. And what's great is because we're dealing with tenths, every time you move from one place value to the next, you are regrouping 10 again. If it's 1 unit, you get 10 dimes or 10 tenths. If it's tenths, you get 10 hundredths. So it's always a 10 to 1 ratio as you're doing it. What you get to see, though, here in the book is they give you, here's the addition. Here is a subtraction problem. And what you can see is someone taking away, and this little arrow down here is indicating take away 0.17, which is all of this stuff, and it leaves behind the rest. Okay. Let's see. What else? What else can I share with you? Those are the big pieces. So what's nice is if you did have 3 and 5 hundredths plus 7 and 23 one thousandths, right? You could look at this. You would never turn this back into improper. I mean, that would just be ridiculous, especially now that we know these are terminating decimals. This would be that number. This would be here. So 3 decimal places because there's 3 zeros. And then we would line up the decimal places and write the numbers out. So again, I will probably put in the additional 0 here that is being adjoined so that when we add everything together, it all lines up. And there's your final answer. Okay, multiplication. Well, multiplication. What do we do when we multiplied fractions, right? So let's get a little white space in here and go back and say, what do we do if you multiply fractions? All right, here we go. So if you're going to multiply some fractions, let's say we have 2/3 times 5/7. What did we do? What did we do with these? Well, yeah, what was great about fraction multiplication is we had a model where we could kind of draw the big rectangle and then take 2/3 of it, but it turned out that it was just multiplying numerators, multiplying denominators, and that gave you something like this pretty quickly. So what I want you to do is I want you to think, if we had numbers that were being multiplied and they were decimal numbers that we could represent as fractions. Okay. So I want you to think, let's do this one. All right, so here we go. Now, if I had these, what I could do is I could just say, I know how to multiply fractions. I multiply straight across. So here, what we could do is say, okay, so this would be 2/10, and that would be 45 hundredths. And when you multiply straight across, 2 times 45 would give you 90. 10 times 100 would be 1,000. My final result has 3 decimal places. So I would write 3 decimal places and then start writing. And I'd put this in. So 0.2 times 0.45 gives you 0.090, not 0.90. It's tempting to say 2 times 45 is 90, and then I got my decimals. Okay. We're not lining up the decimal places here because that's not what the multiplication looks like. However, if you take a look at the denominator, it turns out to be 10 times 100. And if you're counting the zeros, you know you end up with 3 zeros. You had 1 0 to start, you had 2 zeros, so that gave you a total of 3. So you could do that with the decimal places themselves and not worry about that. So there might be a shorter way to come to the side and say 1 decimal place plus 2 decimal places is equal to 3 decimal places. So now I know my answer is going to have 3 decimal places. Now I finished this one up by then looking at the numerator, which is just 2 times 45, which is basically the numbers I had here without any decimal places at all. So as long as you take care of and handle the decimal places at the beginning, this really does just turn back into multiplication like whole numbers. And we're back to chapter 3. So 2 times this, 1 times 0 is 90. Okay, so I have the number 90, but there's 3 decimal places. So put 90 in over here, and then I have to fill in any additional zeros as I go. And that is how you multiply. That's it. That's it. Okay. I mean, I guess we could make it more complicated, but I don't think we need to. It doesn't make any sense. So again, what you can see is how many digits, we add them together because those are going to be zeros in our denominator. And so when you look at the 1 digit, then 2 digits, that's 3. At the end of the day, move 3 decimal places. 2 digits and 3 digits. 2 plus 3 is 5. There's going to be 5 decimal places here. 1, 2, 3, 4, 5. And 0 decimal places and 1 decimal place. That means there's going to be 1 overall. And when I multiply, I get 1. Okay. To be honest, though, like there might be a much easier way to do this than writing out the typical algorithm. Like 1,000, if you did write it as a fraction, this would be 36 tenths. And then you could just kind of say, well, wait a minute. 10 leaves 100, and 100 times 36 is 3,600, and I am done. I don't have to worry about decimal places. So again, totally up to you. Find something that does work for you as you go forward. Okay. All right, so let's see here. The algorithm is suggested. Here's the algorithm. Ignore the decimal places and do the multiplication or divisions as if all numbers were whole numbers. When you're finished, place the decimal place in the result using estimation. So this is a technique that is used as an estimator for the answer. For example, 8.2 multiplied by 2.63. So if you look at this, what they're saying is, hold on. If you multiply these two numbers together, you're going to get this if you ignore all of the decimal places. But 8.2 is about 8, and 2.63, if we round it down, that's 2. So, and if I rounded it up, it's 3, right? So basically this number is between 8 times 2 and 8 times 3. 8 times 2 is 16. 8 times 3 is 24. So I know there's my 16, there's my 24. Looking at this number, I need a number between 16 and 24. So put the decimal in the place that gives you a number between 16 and 24, which would be right here. Again, that does require a decent amount of work. If you had stopped and said, wait a minute, I have one decimal place and 2, and 1 plus 2 is 3, you'd also be able to get over here and say there are 3 decimal places. Okay, so a couple different ways to do it. A couple ways to think about it. The estimation approach at least gives you the idea that you should be thinking about the result. So here's a grade 5 page, shading. What does it look like for 1.5 times 0.5? And you can see it looks almost just like fractions because it really is. It's fraction multiplication. That's all it is. Okay. All right, we're going to get into scientific notation now. Now, depending on your calculator, you may see something different. So scientific notation is, let's see here. Scientific notation is written as the product of a number greater than or equal to 1 and less than 10 and an integer power of 10. Okay, so here's the idea. It looks like this: a times 10 to some power. Okay, and what do we know? The absolute value of a has to be between 1, it can be 1, and no more than 10. So like the number 39, we would write that as 3.9 times 10 to the first power, because we're thinking of it as being multiplied by 10. Okay. So that's the idea. That's what it needs to look like. It needs to look like this. This is scientific notation. This is not. This is sad face. But really, this is just known as standard. Standard notation and scientific notation. Okay. So let's see here. If you see something in scientific notation, you can kind of move it forward and backwards. So again, taking something that's in standard form, putting in scientific, and going back and forth, guarantee that's in the homework. So if you had something that was like this, and this is standard, and we could say put that into scientific notation. Okay, that's over here. There goes that. And if we had scientific notation, 2.7 times 10 to the negative 5. So again, as you're looking at this, our goal is to write this as a number between 1 and 10. So where would you put the decimal? You'd have to put the decimal here. So your scientific notation would be 9.3. And then you just have to think about how many places did you actually have to move the decimal to get it back. So 1, 2, 3, 4. So this would be times 10 to the 4th. I'd go times 10 to the 4th because I'd have to move it to get it back to where it was. Likewise, if we have a negative value, so 2.7. So again, this means I'm dividing by 10 a whole lot, which means it's actually, take this and divide by 10 a whole lot. You have a very, very small number. So what I would do is I'd be moving the decimal point the other direction. 1, 2, 3, 4, and 5. And then what you do is you put zeros in wherever needed. So 0.000027 would be exactly the same. So you've got kind of a forwards and a backwards. All right. Basic scientific notation ideas. And again, you'll have some examples here of taking a number that's in standard form and putting it in scientific notation. And then, of course, you'll get some that go the other direction. Okay, here's scientific notation. And let's see here. Yeah, so here's convert back to standard number. So here's 10 to the negative 5. Think about that. You're dividing by 10 to the 5th. What does that mean? You're making the number much smaller. Here, multiplying by 10 to the 7th. 10 to the 7th is huge. That means I'm going to be making the number bigger. So I move the decimal place to the right to make the number bigger. Here's a negative number, multiplied by 10 to the 4th, again, making the relative size bigger. So the decimal moves to the right. And there we go. They'll put a few in here, maybe working with scientific notation, but not the biggest thing. Let's hear dividing decimals. So again, dividing decimals, honestly, probably the easiest thing to think of is the measurement approach to decimals. That would be absolutely ideal, because then you really don't have to worry about the fractional pieces. Let's take a look at kind of options. So they say up here, let's see here, before taxes on the total cost of 360, the cost of each bottle is 120. How many bottles did she buy? So divide 3.60 by 1.20. So again, making these groups out of the kind of fraction strips. And there's nothing wrong with that, but let's take a look and see if we can't make this a little bit easier on ourselves. So you have a couple of approaches you could use. If you are dividing with decimals and decimals, so some of the texts say move the decimals, okay, but let's actually think about what's happening here, okay? So, and typically they would have a reason for it. They'd say, hey, you want to divide so that your divisor is a whole number. We want that to be a whole number. Okay. So as you're doing your division, I'm going to take this number and I'm going to put a little white space in here, actually. So think here, what you have is 1.2032, and we are dividing by 0.32. Okay? Let's put that in fraction form. This is 12032 divided by, right? 1, 2, 3, 4 digits, 4 decimal places, divided by 32 over 100. Okay. So you have a couple of approaches to this problem. One is to make a common denominator. So make a common denominator, that would be over here. And if you do that, here's what you're going to end up with. You're going to have 12032 over 10,000. This one, we would need to floss by 100 on top and bottom. So this would be 3,200 divided by that same value. Remember, when you divide straight across, this really becomes 12032 divided by 3,200. And you could go do the division with 3,200 divided into 12032, no decimal places anymore at all, and I can just do the division. So that converts everything to whole numbers, everything to integer values. It becomes back to kind of what you've done before. Now, research has shown that may, while it's perfectly fine, that for some reason, the larger this number is, the harder it is for students to do the multiplication. Now, 3,200, you could multiply that by 2 just as easy as you could multiply 32 by 2. But it's good to take a look and say, well, maybe there is a better way. The better way is to take this and use equal quotients. So what we're going to do is we're going to treat this like a fraction over a fraction. 12032 over the 4 zeros. There's the top. And on bottom, 32 over 100. And we're going to multiply by whatever this bottom one is, so that I end up with a nice whole number in the denominator. So I had 2 decimal places, so 100. So if I multiply by 100 on top, 2 zeros go out here, the 100 goes away, and that gives me 12032 over 100, 2 decimal places. So what would it look like here? It would look like 32, but dividing into 2 decimal places, 120.32. Okay. So what this did, this process, when you think about kind of a way of taking where you started, and I'll put that in blue, I started with the decimal place here and here. I multiplied each number by 100 because that way the quotient isn't going to change. Moving this one, multiplying by 100 gives me 32. Multiply it by 100 doesn't give me a whole number, but it'll still be fairly quick and easy to do the division. So process-wise, we do tend to do things that make things a little bit easier, at least whenever possible. So if you prefer to keep your decimal points to the smallest number possible, that's perfectly fine. Then you just move the divisor's decimal point, which every time you move it, you think of multiplying by 10. You can't change things. If you multiply by 10 on the bottom, you got to multiply by 10 on the top. And that's what we're doing here, is we're just kind of making a new value. So when you see something like this, and let's do one of our own. Let's do something like this. I like that one. 9 divided by 0.75. So when I think about this, first off, 9 divided by 0.75, I could think of this as being fractions, right? I really could. It's almost, when I see this, I say, ooh, 9 divided by 0.75, that's 3/4. Well, we already know what to do with this, that we could rewrite this as multiplying by the reciprocal, and my final result is 12, and I'm done. I don't need decimals at all. Totally up to you. Totally up to you. So I'd like to use this quotient piece, and I'd like to also show you some ways that could make it a little bit easier for you. And I think that's really helpful, especially as you become a teacher, trying to find ways that'll help students. So what we're going to do is let's do something that's similar, but not exactly the same. Let's say that we have 7 divided by, okay, and we're going to divide by what? Okay, 0.025, right? What are some ways to do this problem? Well, we can do the traditional way. Traditional way would say write it in the normal division technique. And then if you are missing a decimal place, write one in. I'm just writing that because this would be 7 units or whole numbers. Write that in. Then the traditional way says rewrite by moving the decimal place on the divisor so that you end with a divisor that's a whole number. But if you do that, by doing that, I multiplied by 10, 10, and 10. That's 1,000. I have to do the same over here. I have to move this 3 places. There's nothing written there, so those become zeros. So really, this becomes the problem, 25 into 7,000. Not too bad. Okay. Let's see here. How could I do this? Well, 25 goes into 7 times. Let me change color here. 7 times. 25 goes in there 2 times. 2 times 25 gives me 50. Right. 50 gives me 20. Bring down the next 0, 200. That goes in 4 is 100, so 8. So this becomes 200 minus equals 0. Bring down 0, and it goes in 0 times. So this becomes 280. That is option number 1. This is the traditional approach. Okay. Option number 2, maybe you would like to divide with smaller numbers. So you're going to create equal quotients. Now, you know 25, if I multiply by 2, would give me 50. So I'm going to multiply by 2. And if I do, I have to multiply both of them by 2. So 7 becomes 14. And I get something like this. Why is this perhaps better? Because you're now dividing by a single value. Okay. Let's keep going with it, shall we? Let's keep going. Well, 5 is nice, but isn't it easier to divide by 1? Got it. Let's multiply by 2 again. And this becomes 0.1. But I have to multiply by 2 over here again. So that becomes 28. Now I have 28 divided by 0.1, or divided by 1/10. Now again, I could go through and do the division manually, where I set things up, move the decimal place over, and go. Or I could say it's easier to divide by 1, and I multiply by 10. And if you multiply by 10, what I've done is I've turned this problem into one where I didn't need decimals at all. My final answer is 280, which is exactly the same as we got over here. This is known as equal quotients. Equal quotients. Very nice to have something like this. Very nice. Let's see here. So here's method number 1, the traditional. Method number 2, equal quotients. Method number 3, we'll do fractions. 7 divided by 0.025 becomes 7 divided by 25 over 1,000, 3 decimal places. Let's see here. That's the same thing as 7 divided by, let me simplify this a little bit. 25 goes into 1,000. 25 goes into 104 times, so 1,040 times, divided by 1/40th. So that means it's 7 times 40 over 1, which is 280. And you can see it matches. Many different approaches here. Many. Okay. Let's try another one. Let's try another one. Okay, let's see here. What do I want to do here? 0.05 divided by, I don't know. 0.2, I guess. Make something up here for a problem. So we have a lot of different approaches. I will tackle this one with the traditional approach first. So I would first write this out, and I would move the divisor, which is again the number over here on the left, move this decimal place by, which is really multiplying by 10. Move it over 1. I got to do the same over here. So I will rewrite the problem. This is now 2 divides into 0.5. And then do the division. 2 goes into 0, 0 times. 2 goes into 5, 2 times. 2 times 2 is 4. That gives me a 1. I need another 0, and that's where, because these are fractions, I can just bring another 0 in there. And then, let's see here, 2 goes into 10 5 times. 5 times 2 is 10 minus equals 0, and we're done. And now this is where we have to kind of think about it here. These place values, this was whole groups, so they had to match up, which means that the decimal place has to be located in the right above where the decimal place is. So if you do this little move it over technique, it's always going to line up like this. So this would equal 0.25. If you want to check it, 0.25 times 0.2, right? What does this become? It becomes 2 times 25, right? 50. But I have 1, 2, and 1, which is 3 decimal places, which is 0. Let's see here. Oh, yep, 0.050. And that matches what I should get. So I can check it with multiplication and it works out. That's the traditional approach. Let's see here. Shall we try a few of the other approaches? That's number 1. Number 2, I don't like dividing by 0.2. I'd rather divide by 1. So I'm going to take 2, because 2 times 5 is 10. So that's going to help out. So I would rewrite this divided by 0.2, and I would multiply both of them by 5. Love that property. 0.25 divided by 1, and anything divided by 1 is itself. You are done. Let's try number 3. Turn them all into fractions. So this becomes 5 over 100 divided by 2 over 10. I could then turn this into 5 over 100 times 10 over 2. The 10 goes in here 10 times, right? The 5 goes into 10. What is that? 2 times? So my answer is 1/4. If you want to put that in fraction form, 1/4 becomes 0.25. Now that's the invert and multiply approach. If you prefer, you could have rewritten this one as 5 over 100 divided by 20 over 100. Got a common denominator. Okay. And what does this equal? Why, that equals 5 over 20. And then all you'd have to do is say, well, I need to get this into decimal form. Either divide here with whole numbers, 20 into 5, or multiply to give yourself a power of 10. Now remember, this goes from section 7.1. This is 2 squared times 5. I need one more 5 to make 2 squared times 5 squared, which is 10 squared. So this becomes 25 over 100, and in decimal form, we get 0.25. So quite a few ways to do these. I'll let you take your pick. Again, no preference on my end. It's whatever works best for you. Sometimes there's like a more efficient way, but that's, again, kind of up to you as you do it. Okay. All right. Yeah, here we've got division resulting in a non-zero remainder. When we get to non-zero remainders, those are really going to come up with repeated decimals, which is the next section, 7.3. So we're not going to worry too much about those as we do it. Okay. Mental computation. So this is estimating decimals, decimal notation, and the properties. So kind of understanding where are kind of the important pieces. If you're doing mental computation, your goal is to get the right answer. You're not estimating it. So you'll notice what they sometimes do is this technique of breaking off and bridging says start with 1.5 and then add the whole number part. See that? Then once you have that whole number part, then add in the fractional part. Then add in the whole number part again. And when you're done, add in the fractional part. And that's breaking up and bridging. Yeah, they have a whole piece here on using compatible numbers. I'm going to tell you that it's pretty rare. Look, if it happens, use it. Like here's like 91 cents. I'll put that with 9 more cents to make an additional dollar, right? So then 7 plus 4 is 11 plus a dollar gets me 12. So you can see how they came up here and got 12, which again is great. But how many times are you going to get 0.91 and 0.09? Like it just works out perfect. I don't. It's really rare to use that. Let's see if they have compatible numbers. Making compatible numbers is probably better. Making compatible numbers is making numbers that are going to add together quickly and easily and then leave the additional pieces until the end. So find things that work together quickly, 20s, 25s, things like that, 50s, anything like that where you can add them very quickly in your mind, that helps make a compatible number. Okay. Let's see here. So again, what are other ways to do this if you were trying to do this mentally? I probably would do something like this, just because that's that's me. I don't need to change anything, because I could also get 1297 very quickly from this because there's really no regrouping even in that first place. And then I still need to add my 9 cents on. So I just basically saved the 9 cents in my head for a moment, but 9 cents is really 10 cents minus 1 cent. So watch, if you do this, you can come down here and take this, add a dime to it, and that gives you 13.07, and then take off a penny. Now it's quick and easy to take off the penny, and you get 13.06. Right? What else? Balancing in decimals in subtraction. Yeah, this is basically what we've done before, right? If I had 4.63 and I'm subtracting 1.97, I do not want to do all of the cross outs. I know it's coming. I know the regroupings are coming, but I just don't want to. So I'll just add 3 cents to each. And when I do that, it recreates the problem as 4.66 minus 2.00. And I got to tell you, it's so much quicker to do that problem. All the tools and techniques we've done to this point in time are fair game here. Every one of them. Why not? If you don't like doing division with 0.25 because 25 is too big of a number, multiply by something to make it easier on yourself. It's going to be much more convenient and probably make fewer errors. When it says balancing with decimals in division uses the property, you can multiply on top and bottom by the same non-zero number, which is known as, anybody? Anybody? Why can I just multiply on top and bottom? That's right, from chapter 6, 6.1, the fundamental law of fractions. It's still here, and it's making things easier every time we use it. All right, let's see, what else do we have here? Rounding decimals. Okay. Let's see here. Yeah. Um, Rounding's not bad. Just remember place value wise, just like when we were rounding whole numbers. So make sure you understand which place value you're going to. If you are going to the nearest tenth, then write the number out. This tenth is what we're looking at. So if you were looking at a number line, here would be 7 and 4/10. Here would be 7 and 5/10. And then everything else in the middle, like you could think of this as having the extra digits here. Where is this number on that number line? Right here in the middle would be 7.450. And you can see this one's above it. So if I was rounding means which of these numbers would you choose? It doesn't have all the digits, but is close. Which of these two would you choose? And you want to choose the one that minimizes your error. So this distance is smaller. This distance is larger. So rounding, I would choose 7.500. And honestly, really just 7.5 as my final rounded number. And you can see them doing the same thing. So keep that in mind. If it is right halfway between, to be technically honest, you are just fine going either direction. We have a convention that says we go one direction, but we're as wrong as anything else. So just kind of keep that in mind as you're doing it. Yep, that's about it. They did some estimating here. They're showing a few more estimating pieces. If you're looking at these, kind of being able to do some quick rule of thumb stuff is fairly convenient. And so this one's about lightning. And if you know the sound travels at 0.33 kilometers per second, 0.33 is basically 0.3, right? Pretty close to that. So if you have that and you hear thunder 3.2 seconds later, which when you multiply these two numbers together, 0.33 and I would probably say 3.3 because you're really close to a 1/3 and multiply by 3. So you're pretty close to saying this is about 1 kilometer away. Okay. So again, just a quick rule of thumb as you're kind of going through and doing these. Being able to find a good estimate is pretty quick. You can do that as well. We'll do more with these in percents as you take a look at it. Quick rule of thumb when you're doing gallons of gas, right? Like what's my miles per gallon? How can I figure that out? Get yourself some nice numbers. Sometimes it's a lot easier when you use those compatible numbers. And don't forget round off errors. When you round things off, you are creating an error because it's no longer this exact value. Now, you have to be careful. You only want to round once. Here's the reason why. If you had a number like 3.4445, and I said round to the nearest thousandth, you would look at this digit, and our convention is to round that one up. So that would make the number 3.445. But if I now say round to the nearest hundredth, this 5 would round that up. Becomes 3.45. If I say round to the nearest tenth, this one rounds it up. Now you get 3.5. I say round this up, and you end up with 4. So if you keep rounding to different values, the end result may not be that close to what you would have seen at first. It might actually create more error. Indeed, on a number line between 3 and 4, 3.4445, here's 3.5, is somewhere over here. I would have rounded that direction. Okay. But if I round and then take the rounded number and round again, take the rounded and round again, I create enough error that it actually makes it look like it'd be better to go that direction. So when you are rounding or computing and then rounding, you want to do all your computations and then round once. Do not round multiple times in a problem. Okay. When computations are done with approximate numbers, the final result should not be reported using more significant digits than the number with the fewest significant digits. This is something that you'll see in a chemistry class as well. So this is kind of the rule that we use. Many times in mathematics, we do different than in science. We would actually say keep all the values and then simply round at the end of the day, indicating that there are no additional values to be added. All right, that wraps it up for 7.2. Hopefully that gives you a good leg up. Operations on decimals are almost, when you get used to it, it's almost like just back to chapter 3. It's almost just like whole numbers, really. Line things up. It's just place value. So, all right, love it. Off you go.